So guys, welcome back to Chemistry Ado. First of all, I'm extremely apologetic for not uploading for the past 2 weeks because of some college commitments that I needed to fulfill. However, they are now done and we'll get back to our course. So last time we did distillation, we did fractional distillation, we did some uses of fractional distillation, we did decanting, we did centrifugation, we did dissolving, filtration, evaporation, slash crystallization, and we did filtration and crystallization separately as well. Alright, so now they're done. Now let's move on to the other technique, that's chromatography. Alright. So chromatography is a technique that is based upon difference in solubility, right? And we're going to manipulate this difference in solubility, right? And I'll actually show you that. Now what's so special about chromatography is that it's a separation and analysis technique only. Other techniques were separation and collection techniques. But here, you can only analyze the substance, you cannot collect different components of a substance, right? So let's get started. So it's a technique that is based on difference in solubility. Alright, as distillation was based on difference in boiling point. So difference in solubility. Alright. Next, um, it's a technique that is only a separation and analysis technique. An analysis technique. And how do we analyze or separate substances in this technique? By manipulating the difference in solubility. Alright. Now coming to the meaning of the word chromos that you'll find in some books. Chromos means colors. Means colors. Alright. So you'll see there's we'll actually have colors in the technique, and I'll show you that as well. All right, so first of all, how is it performed? All right, so let's say you have a beaker and you have a filter paper. All right, and you have a sample, for example a food sample in a petri dish that you want to analyze. Let's say it's a liquid. That will be easy. We can do it on solids as well after dissolving them. All right, let's say it's a petri dish in which you have a food sample. All right, now what you do is that by taking a dropper, you put a drop here. All right, and draw a baseline with pencil, not pen, where you have placed the spot. All right, it's very important for you to draw this baseline with pencil. So this is the baseline, and I'll write specifically pencil with it, not a pen, not ink. You do not use ink, and I'll tell you the reason. So you use a solvent. Now it's important to keep the solvent level below the baseline. All right. So this is some solvent, and you keep it below the baseline. All right. And as I told you before, this is filter paper. Now, why did you draw the baseline with pencil and not ink? So the question is, the question was that why is baseline drawn with a pencil? With a pencil, right? Why not ink? So the reason is that if you draw a baseline with ink, it will disrupt the results. Why? Because ink also splits into its components. So baseline with ink will disrupt the results, and ink will separate into its components. Ink is also a mixture, alright? So it will separate into its components. Now, this solvent you're using, alright, it needs to have some properties, alright? So what are the properties of the solvent? So first of all, this solvent needs to be insoluble. Oh, sorry, soluble. What do I mean by soluble? That it must have the ability to dissolve the components of this spot. Alright? If some substance has not has no ability to dissolve the components in the spot, then the chromatography will be useless. It won't happen even. So it needs to be soluble, right? And next, it needs to be non-reactive. If it reacts with the components of the spot, then it will be a problem because a chemical reaction will occur and it will disrupt the results. All right. Now what we actually do is that we allow the solvent to travel, so it travels along the paper through diffusion, and what happens is at some point we draw a solvent level. All right. This is solvent level or solvent front. This is the solvent level. This is the solvent front, right? Okay, so that's the properties of the solvent. Now let's move on to the calculation. So let's say we move on to RF value. All right, so there's some calculations that we do, and that are known as the RF value. All right, now what is the RF value? So basically, when you're asked about its definition, what you need to write is the ratio of distance traveled by distance traveled by salute to distance traveled by solvent. All right, now what is what does that mean? For example, this was the filter paper or the chromatogram. Remember that filter paper on which chromatography has occurred already is known as a chromatogram. So first it was a filter paper, then after chromatography, it's known as a chromatogram. Okay, so what I do is that I draw a spot, not draw the spot, I release it for dropper. All right, a spot. I put it under a solvent. All right, now this will rise, and what happens is that we see a spot. All right, now what does this show actually is that a component of this spot had dissolved in the solvent and it has reached its maximum solubility, and now a spot has been made and it will separate. Now we'll observe a color. For let's say I'll observe red here, then uh, the second component dissolves and it shows green color, and then the third component dissolves and shows blue color, let's just say. All right, and after that no color change is observed. So what I do is that I draw a solvent front here. All right, now this is the maximum distance the solvent has traveled, and these are the individual distances that the solutes have traveled. All right, it just says this is A, this is B, this is C. All right, and I don't think you'll notice the difference, but let's just say the distance from the baseline to the solvent front is D. Alright, so what I'll do is that I'll calculate the ratios. Alright, so let's just say the ratio RF value of red All right, but let's just write with red. Okay, so RF value of red. RF value of red would be A divided by D. RF value of green will be B divided by D. RF value of blue would be C divided by D. Now, if I ask you which of the substances, red, blue, or green, do you think is the most soluble? Now, just think and try to give me an answer. Alright, I believe that you must have come to an answer. So, the most soluble among them would be blue. Why? Because it travels the maximum distance with respect to the distance of the solvent. Alright, so that's why it has the highest solubility. Alright, so there's a so greater the RF, the greater the solubility, and remember that RF can never be less than one, will greater than one. Alright, it will always be less than one. Okay, so next I need to discuss with you some different types of chromatographies. Alright, so let's get started with that. Okay, so first of all, the ascending chromatography, the chromatography that we normally do, that we normally show you, not do. We don't do it normally. Okay, so what we do is that here's the chromatogram or the filter paper, right? Here's the solvent front, here's the baseline, here was the spot. I'll show it with an X because it will disappear eventually because of the components being dissolved. And we put the solvent level below the baseline. Alright, that's how we do it in ascending chromatography. And remember, this method is more accurate than descending one. This is slower, however. I'll show you why. But it requires a shorter filter paper. Shorter filter paper required. On the other hand, the descending chromatography. Descending chromatography. Alright. So when it comes to descending chromatography, what we do is that we take an inverted beaker, we close it up. Here's the filter paper. Alright. Here's the solvent level. Here's the baseline. Here's the spot. We allow it to occur, the process to occur. Now, this is a faster process, agreed. This is what we normally do because of its speed, but it's less accurate. Why? It's less accurate because it's gravity fed. Molecular water slip because of gravity. Alright, and also it requires a longer filter paper. Right? Great. Next we have the radial photography. Radial chromatography. Okay. What I do is that I take a filter paper that is round, alright, and I put a spot in the middle. Right, so let's say here I put the spot and I add the solvent through a dropper. Alright, so I add the solvent through a dropper at the spot and I see colors to form here in a radial fashion. Alright. And after all the colors have appeared, I draw the solvent front, right? So let's say I draw the solvent front somewhere here. It's not a very good drawing, I agree, but we'll have to work with it. Alright, so what I do is that I take the distance. For example, I want to calculate the RF of the second color. Let's just say this distance is B, this distance is B, and then I take the distance till the solvent front. Let's say this is D, so the RF would be B over D. Alright, so this is another method of doing chromatography. Alright, but there are some things that you need to keep in mind. First of all, what if I use a volatile liquid as a solvent? It will not always be water. Alright, so it can be any volatile liquid. Let's just say I use ethanol for my experiments. Ethanol is volatile. So what will I do? So what we should do actually is carry out chromatography in a closed container. Chromatography in a closed container. Now, what will happen is that at some point the container will get saturated with the vapors and no more evaporation could occur. All right, so the liquid will start rising. All right, so the problem with volatile liquids is that before they could even rise they evaporate. So if we do it in a closed box, actually what will happen is that the box will be saturated at some point and then we'll be able to carry out the process. All right, so for saturated or volatile liquids. Next, solvent level must always be below baseline. Be below baseline. Now there's also a reason for it because it prevents the spot from itself dissolving. Alright, we need the components to dissolve. If we actually put the solvent level above the spot, then the spot will get dissolved inside the solvent in the beaker. To prevent spot from dissolving in beaker. All right, next, what if I have chromatography in which I have components that are colorless? All right, then what will I do? So we actually use locating agents. So spray locating agents. In case of colorless solutes, right? Now, what's an example of locating agent? Ninhydrin spray is a famous example, or NaOH if we are using metal ions. So you need to remember ninhydrin spray. It's actually a wonderful locating agent. That's all for ascending, descending, and radial chromatography. There is another chromatography that we use, and that is the two-way chromatography. But it's not very much found in your syllabus, and no question has been asked on it. So you can research it up. It's not a very difficult topic. It's actually fun. What we do is that we take a filter paper, and let's just say that we are using a sample that requires two solvents. So what we'll do is, now we can't use a mixture of solvents because the problem with the mixture of solvents is that we won't be able to calculate the RF very well. Alright, so this is the solvent level. What we do is, for example, this spot is made, and we observe a bigger spot here. Now what this bigger spot means is that there are 2 to 3 solvents inside of it. Alright, solutes inside of it. So what I'll do is that I draw another baseline here and dissolve it in another solvent in which I believe it would be soluble. And if these spots are soluble, then they will also travel. All right, but it will surely break down to its components. All right, and we can actually carry out the process. Now, for example, if there was a solvent, there was a solute that traveled in the first solvent but was insoluble in the other one, it will be like the one I am highlighting here. All right. Now, next there are some uses of chromatography that I need to mention. So, uses of chromatography. First of all, it's used in food tests. Next, it's used in urine tests in medical industry. Urine tests for diabetes or any such substances inside the urine that could be tested. Next, these are all the uses of chromatography that you need to know. All right. Next, we'll move on to the topics of collection and nature of gases. All right. So be stay tuned for the next video. It will be coming out very shortly, and I promise it won't delay.